diffusion and effusion. In this video, we'll first define effusion and diffusion, and then talk about the differences between the two of them. We'll learn about one of the applications for effusion that I think is particularly interesting, and then we'll use the formulas in the previous video that we learned to derive a formula for the relationship of the mass, the speeds, and the rates of effusion. And then, of course, we'll solve problems using this equation. So first of all, what are these two things? Diffusion you may already be familiar with from previous science classes. So this is when things are combined and then they mix. They kind of run into each other. So this would be a picture scenario like this, where we have two gases and then we release them and we let them mix together. That's very different than what effusion is. Effusion is when you have gas that is going from one container that is under pressure, and then it goes into or through a small opening into a completely empty container. So there isn't any gas molecules in the other. That's what effusion is. So a situation like this. So you can see how through these two pictures show you these are not exactly the same thing, even though they are relatively similar. So now let's talk about one possible use for this. So one use for effusion is isotopic enrichment. So there's lots of applications where you need one isotope of a particular atom and not the other one. And these are very hard to separate because chemically they're very nearly identical. So they have the same number of electrons, the same number of protons, and so to separate these, the only real difference between them are their masses. And so you need to have something that separates by mass, which, given the fact that effusion happens faster for less mass and slower for things with more mass, this gives you a way to separate out isotopes. So what you can do is you can have a chamber filled with gas. And here, because I can't really show you visually the difference in masses, what I've shown you instead is I've sort of dramatically exaggerated the difference by showing you a small and a large. Keep in mind, for isotope enrichment, these are actually the same size. They're just different masses. So what you would do is you would allow a membrane with some holes through it. And so effusion would be able to happen here. You'd have effusion going on. The lighter particles, here represented by the smaller molecules, would go through a lot faster. They would effuse a lot faster. Now, of course, the heavier molecules would also effuse, but at a slower rate. So now what would happen is you would get this new sample of gas that has more of the lighter particles than the heavy one. And you would either take this out, or more likely you would have this be in some sort of flowing chamber where it flow into the next stage. And now you do it again. And so you have this time a higher percentage of your lighter particles than your heavier ones. And you can again separate this out. And perhaps this takes many stages sometimes, but if you do it enough times, you can get a nicely separated sample with your lighter particles, here represented by being smaller, being mostly separated from your heavy particles, here represented by being larger. So this is an example of this where it's 4,000 stages long. So here I have represented one stage. This is 4,000 stages long, half-mile long, 6 stories high, and this is an enrichment facility that's in Tennessee where they're enriching uranium. And the reason you have to enrich uranium is that 90% of it needs to be U-235. But the problem with that is if you just take a normal sample of uranium, only about 0.7205% of it is actually U-235. So you need to separate out all the other isotopes so that you just get the one that you need for your nuclear power plants. Now let's work a little bit on how to go through and do some math with this. We have URMS. We have our equation for that we derived in the last video. We can solve this for temperature instead now. So we just rearrange, we square everything, multiply up, divide down. Now, for two different species at the same temperature, this has to be true because the temperature is going to be the same if we say it is. And so I set them equal to each other. I take this equation and I make two of them, and I put some subscripts on anything that changes. So if I change my particle, my atom, my molecule, I'm going to change my RMS, and so I put a little subscript here. And I'm going to change my mass, so I put a little subscript here. Notice we still have this 3R. I didn't put subscripts because R doesn't change, 3 doesn't change. And now what we can do is we can say, well, wait, if we have 3R here and 3R here, those cancel away, leaving us with just this numerator. And now we can rearrange this. So why would I want to do this? Well, let's do one more further rearrangement, and I think you'll see. So now I've taken the square root of both sides, and so we have this ratio of the speed of the ratio of the speeds of the molecules equal to the ratio of the masses. Now notice these are inversely proportional, right? So we have R1 here and M1 here. That comes from this rearrangement of this. You would divide that down here and divide this down here. So this is saying the same thing that we've already said multiple times, but now relating it to effusion too. So if you take and you raise the mass of a particle, you lower its speed, which means that their masses can form a ratio with their speeds. Something that's moving faster is going to effuse faster, so this also gives us the ratio of the rate of effusion. So let's do an example of this. I tell you that a gas effuses 1.55 times faster than propane. We know what propane is, C3H8, at the same temperature and pressure. So that's just setting up your situation so you know that you're not changing your temperature or your pressure in this case. The measurements were done at the same temperature and pressure. Is the gas heavier or lighter? What is the molar mass? So if this gas is going to be effusing faster, it means that its speed, its average speed, its RMS is faster, which means that it has to be lighter overall in order to have the faster speeds. Now, when we want to look and say, well, okay, how much faster is it going? And that's our measurement of the molar mass. So we take the equation that we learned on the last slide that relates the two. And we say, well, our R1 over our R2 is equal to the square root of those molecular masses. Being careful to note that the 2 is down here and up here. The 1 is here and down here. Okay, so now we don't actually have an R1 and an R2, but what we do have is a ratio. By saying 1.55. And now we just have to be very careful about where we put what mass. So since this is over 1, that means that our faster one is on top, because this R1 is larger than R2. So since our faster one for the speeds are on top, we know that our unknown mass will be on the bottom because they are inversely related. So then we can put our molecular mass of propane on top, rearrange and solve to get 19.6 grams per mole. Now let's do another example. What is the ratio of the rate of effusion of the most abundant gas, N2, to the lightest gas, H2? So this is, again, using the same equation that we did before. We know our R1 and R2 are inversely related to their masses. And at this point, since we just need to know the ratio of the two, we can go ahead and fill in. Now we do have to be careful with the wording of the problem. I asked for the most abundant gas to the lightest gas, which means that the N2 goes on top, the H2 goes on the bottom. So when we go to do their masses, we'll put the 28 down here and the 2.02 here. You'll notice I'll be a little bit lazy about putting units, and that's okay because we're solving for a ratio, so we know that they cancel. So I'm going to be a little bit lazy about that on purpose just to show you that it's okay. And when we get done, we get our ratio of 0.269. Since it's a ratio, there's no unit, so we can leave it like this. Okay, now let's do another one that's a little bit more conceptual. So I say rank the following in order of increasing speed of effusion and increasing time of effusion. So far we've been doing speeds, so I want to keep doing that and start with speed of effusion. So here, if we want to know increasing speed of effusion, that means we're going to start off with our slowest. So if we're going to start off with our slowest, that means we need to start off with our heaviest. So we look at our periodic table, we add up all of our masses, and we see that N2O5 is going to be our heaviest, followed by argon, NO, and N2. Now, if that's increasing speed, we need to do the other part and say, what about increasing time? If something effuses very quickly, that means that it's going to take very little time to effuse. So our fastest molecule will have our lowest amount of time. And so it works exactly in reverse. Our fastest molecule is nitrogen, followed by NO, followed by argon, followed by N2O5. So it's all about ranking it in order of masses and then paying very close attention to whether you're talking about speed of effusion or whether you're talking about increasing time of effusion. One more example for this. So it takes 12.6 seconds for a certain amount of CO to effuse through a pinhole. Under the exact same conditions, how long would it take for that much CO2 to effuse? So no different than before. We write out our equation. Now what we need to think about though is how that relates to time, because I didn't give you rate of effusion, I didn't give you speed, I gave you how much time it takes. Now we saw on the last slide that time is related to mass as well because it's related to the speed. And so if something is very heavy, it's going to be very slow, and therefore it's going to take a very long time in order to effuse. So I'll say that one more time. Something is very heavy, and so it is very slow, and it takes a very long time. So therefore, that heavy molecule takes a long time, and so time is proportional to mass. So we're going to take and use this for this equation. So we can fill in our molecular masses. Here I put CO on top, or excuse me, CO2 on top. And so because of that, my CO2 time goes on top, my CO time goes on the bottom, and I solve for T2. And one more further example. This one won't be too much different than the other ones, still using ratios, but now we have a little bit different sets of information. So now I've given you the temperature. So at what temperature will a molecule of uranium hexafluoride have the same average speed as a molecule of the lightest gas, hydrogen? So here we have to go back to that original place that we got that derivation of R1 to mass. And the way that we got that before is by taking our RMS speeds and putting them equal to each other. And we could do the same thing here. And we can cross out anything that's constant. And in order to get rid of the square root, because it's on both sides, we can square both sides, leaving us with this proportion. So now we can either rearrange or we can just fill in. Either is fine. We round to the proper sig figs, needing scientific notation to do so. And we are done with that problem. So in summary, now we know what effusion and diffusion are. We know that they're different because effusion is going into an empty space, while diffusion is two gases or liquids mixing. We also learned how isotopic enrichment occurs because that's one of the main uses for effusion. Of course, there are many others as well. Now, we've also used all the formulas in the previous video along with just relating them in new ways, setting them equal to each other, to derive relationships for the mass, the speeds, and then the rate of effusion. And we've solved problems using all of these different ratios that we've come up with using that square root of 3/2 RT over N formula.